pre-salt, which is a large area offshore Brazil where we have a lot of production of oil, and oil mostly. And it's very important for the development of the natural resources. This picture you see here, this composite, summarizes what we are trying to do here today. There are 4 aspects to this presentation. First, we want to be clear that there's a lot of production going on offshore. Not everybody is that aware of that, but it's one of the fields, the Lula field, and that will come a few times in this presentation, is reaching a production of 1 million barrels of oil per day, which is a huge number. I think it's the largest offshore deep water oil field in the world, and has been developed very quickly by Petrobras and their partners, and Shell is one of them. So we have a lot of production. The mechanisms for production of the oil are complicated. So we use this technique of water alternating gas, you say WAGI, and it's a method in which you can extract the oil better, and also you can use the gas that is already contained in the reservoirs, a lot of CO2 in these reservoirs, so they cannot really be exported. So one thing to do is use them to improve that production. We have geophysical methods, and we'll talk about those today. Many, the picture you see there, we'll discuss it in detail, has all kinds of things that can be applied, and some of them will be more or less useful. The last thing, the petrophysics part of this title, is that we have complicated reservoirs. We have carbonates, which are much more difficult and complicated than the siliciclastic reservoirs in other places. And that's where the geology and petrophysics come together. So we have a problem of reservoir engineering, how to produce reservoirs. We have a problem of geophysics, how to monitor them. And we have a problem of geology and petrophysics, how to understand them. All of that comes together. So we'll try to get to all of that a little bit today. So this first, this map on the left is offshore here, very, very nearby. You probably can see Rio de Janeiro. And this is an area where, since 2 years ago, there's a lot more activity because the laws were changed to allow other operators besides Petrobras. So historically, it was the only one that allowed. So with that, they also allowed schedule these licensing rounds for these other operators to come and bid for the blocks. So that has happened, and now there are from 1, they used to be Petrobras, now there are 6. So Shell is an operator of one of the blocks, or several, and we have also Exxon, BP, Total, and Equinor. So it's something that suddenly becomes much more active. In the whole chain of activities, because now any vendor that sells anything can go to 6 buyers, whereas before it was only 1. So that changes everything, including seismic and everything that you can think of. So there's a lot of activity. The fields have developed quickly because of this use of these vessels, the FPSOs. So they're in principle remote by local standards, maybe 100 or 200 kilometers from the coast, so there's not a lot of infrastructure. So having a vessel that comes and is attached to the wells and stores the oil temporarily until it can be transported to another one to shore, that is speeds up the whole thing. So that's why they're going on quickly. I mentioned already that the recovery schemes are complicated, so you need to do something to see where the fluids are going. And in our case, in my case, that is using seismic, 4D seismic. The role of 4D seismic, I say here that is recognized. Well, that was even before it was proven. So we expected that 4D seismic was going to be useful, and now we know, and I will show you an example of that in a couple of minutes. This increasing activity favors everyone, because you're all here, and you probably want to get a job with one of these companies, and suddenly you have all these potential employers. Okay, so it's a big chain of economic dynamism. Okay, this picture, it's one that when I was in manager of R&D of seismic monitoring, we made this picture a few years ago. I showed this for the first time 2 years ago at a congress here at SPGF. And I will explain a few of the techniques that you see here in a little while. But what you can see here is a cartoon of the sea on the top. And then below that you have the sea, the water, and below that you have the subsurface. And you will see that we have sensors which can be placed on the sea surface, on the seabed, or inside boreholes. You also have some sensors which are permanent, some of them are retrievable, and some of them are semi-permanent. So you leave them there for up to years and then you retrieve them later. So different kinds of technologies. For seismic, you also need sources, seismic sources, and they are the ones that everybody knows about, large ones, but we also are experimenting with smaller ones because we have some strong constraint on the environmental requirements. The IBAMA prefers that we use smaller and smaller sources with time, and they also have a restriction that they do not allow surveys with simultaneous sources. So if you could have those, like 2 seismic boats at the same time, the survey will go more quickly. But that is not allowed in Brazil so far. It is allowed in other countries. So we are thinking about ways in which that can be somehow introduced, and you have to compromise in one way, and one way is to decrease the size of those seismic sources. And there are other things here that we'll get to. But the bottom line is that the objective of this whole thing is that's what I write there, is to look at where gas and water, how they are going from one well to another, because here we're injecting. So if we have what we call breakthrough, so if you inject water and you're expecting that will push the oil to the producer over years, but suddenly in 2 years it gets there, then it short-circuits the whole thing, and that water injector is no longer efficient or useful. It also happens with gas. You want the gas in the water to slowly move this oil to the producers, but if there are layers which are very permeable, the gas can go over them, and then you have a breakthrough, we call it. And we need to see that before it happens. When it happens, there's nothing you can do about that. But you need to see that it's approaching. If you could see that, then maybe you can do something. Maybe you can push less water or gas in that direction, maybe in some other direction, or you can try to control things. So that's what we're trying to do with these measurements. We also want to optimize the rates at which these wells are being produced or injected, because even if you don't have these breakthroughs, you still can try to synchronize things better. And that's all the realm of reservoir engineering. And then often it happens that once you place all your wells, later you realize that, well, they are not all in the optimal places. So you go back and you put more wells, and call those infill wells. You really like to know where they would go, because then you have a better chance of recovering more of the hydrocarbons. Okay, so we'll go a few of these. Top right, this is a mixed audience, so I'm not sure how much all you know about seismic, so we'll do a little tutorial here. So that one that is in red is the standard seismic. We call that narrow azimuth. So you have a seismic vessel there in red, and these streamers behind with the red dots. They usually are 6 kilometers or longer, 8, 10, 12, that they are towed by the vessel. And those are hydrophones that are sensing the seismic waves. So this is the standard way you can do seismic, and has been used a lot over the world. And it is the workhorse for seismic acquisition in Brazil now. So it's convenient, you can do it, cover large areas, and it's inexpensive. The only problem is that it's not good enough, because we have the problem of salt here. We're talking about the pre-salt. We have very large bodies of salt that cover everything. So the reservoirs are right below the base of the salt. And this salt can be, so the water maybe 2,000 meters thick, and then you have some sediment, and then you have maybe another 2,000 meters of salt, which is not a block, but it's varying in topography. And then below that, you have the reservoir. And so if you know about wave propagation, it's going to be a lot of bending and twisting, and then by the time you get to the reservoir, the images are difficult to get. Especially if you're looking at the subsurface only from one direction, like these vessels would do. So what you need to do is look from other directions. And this is where this OBN comes in, ocean bottom nodes. So these are seismic receivers that you place on the seabed temporarily when you do your survey, typically on a grid, maybe about 400 meters apart, so you cover some area. And then once they're laid down, then you have your seismic vessel shooting over it, or a very dense grid. So typically on the seabed, maybe every 400 meters, maybe 500, depending on the area you want to cover, the resolution you want. And then the seismic source is very, very fine, every 50 meters usually. So it's a whole carpet. The advantage of that is that you are now looking at a point, at each point in the subsurface from all directions. Because the node is sitting there, and your seismic boat goes back and forth, and it can shoot energy from all directions. So that has two advantages. The first is that there's a lot more energy that is being used, because it's coming from all directions, so you add up the energy. And the second one is also because it comes from all directions. So since the salt is complicated, you get to look from different sides. So that is the key thing about this ocean bottom nodes, which will give you what people call full azimuth seismic, another name for that. So really important. Many, in the last 2 or 3 years, there are now many of these surveys in Brazil, so many that there's not enough opportunity to do them because they're competing. The companies are lining up, and they have to compete for permits, and they have to compete with these other surveys with the first technique because they also want to be in there. So it gets really crowded. But that is the technique that has been successful, and there will be a lot more of that. If you want to do 4D seismic, okay, so I'll go back to that one. So what you need to do is that once you do your survey on some year, you acquired data, you made your images, you come back later, maybe 2 years later, 3 years later, and you repeat the whole thing. You get another image. And then we difference the two and see what's changing, which is the concept of 4D seismic. It has been developed and proven in many, many, many places around the world. But in Brazil, the pre-salt, just now, for the first time, it has been demonstrated, because all the complexities we talked about. So that, I think, is out of the way now, and we'll see an example. Where we don't have salt, when we have, for instance, the Santos Basin, the seismic, 4D seismic signals are very, very high, and you can see them without having to worry about nodes or anything. It's very strong. So Petrobras has done many, many 4D seismic surveys in that area, and that's all working great. But for the pre-salt, you really need to try harder. So you go back later with your nodes, you try to put them in the same place, because it's important. For 4D seismic, you have to repeat everything exactly the same way. Anything that you don't repeat, let's say you're not too sure about where you put it to begin with. So, yeah, you know it's every 400 meters, but no, you don't know where anything is on the seabed. There's no GPS. You got to find a way to do that. So there are techniques to try to position things or to know where they are. But they are involved in the data itself. You don't. Sometimes the nodes leave an imprint. You come back years later and it's still there. You can put it in the same place. So they try hard and they can reproduce, but not perfectly. Every time you make an error like that of a few meters, that creates a difference in your seismic between the baseline and the monitor, which is a noise. We call that a 4D noise. Most of the time, that's not important because the signals are so big that you don't worry about these little noises. But in the pre-salt, we'll see the signals are also small. So you have to work harder than that. So for that then, what you can do, and this is the best thing to do, is to leave the sensors permanently there. Okay, so there are different ways of doing that. What you see there now goes by the acronym of PRM, Permanent Reservoir Monitoring. This is a technique where you lay sensors which are inside a cable that goes around, and maybe 100 kilometers long, and it just sits there and can last in principle for 25 years, and is connected by an umbilical to some surface vessel or platform. And every time you want to have a seismic survey, you just bring the seismic boat because the sensors are there fixed. Okay? So that helps with not having to put things back in the same place because they don't move. That's a good thing. Unfortunately, these systems are not always very reliable. So they sell them to you with saying they will last for 25 years, and none of them have lasted that long. In Brazil, actually, there are 2. There are, in this whole world, maybe 7, and 2 of them happen to be in Brazil. There are in this other basin where the signals are big, so when you really don't need them, but that's where they exist. So Shell has one, and Petrobras has one. And I think the Petrobras system is no longer operating, it's the Jubarte, and the Shell one is operating, it's in the BC10 area, we call that Old North. And we have done many, many surveys to repeat, and you see high quality 4D seismic, which is great to have, but you don't really need this sophisticated system. But anyway, there are advances in these systems today, and they are now made of fiber optic cables, so they are more reliable, and that could happen would improve the development in the future. There are complications because usually the fields have a lot of infrastructure on the seabed, a lot of things. They are all of the wells in these fields are what we call subsea. They are not connected to the platform. They are so there's something that goes down to the seabed and then it spreads out. There are flow lines. If you want to put your seismic cables, they have to be on top of that. So the problem is that you have to replace any of it. The seismic cable may not last forever, and all the oil field equipment also needs attention. So you need to go and do that. You have a problem. There are two sets of cables. Okay, so that is an issue. So it has a limitation. We continue. I will briefly talk about this other system, which is where you have permanent sensors, but they are nodes. They are not attached to cables, so you put them where you want. What we talked about before, 400 meters. You can also put them in 400 meters, but you leave them there in place. We have a project that will allow them to stay there for 5 years. And then you can acquire your seismic when you like. And then they don't move, so that helps with the 4D seismic. And they are not in the way of the other cables. That's an advantage. We'll discuss that a little later. So that's one thing you can do. And there are more things you can do. This one here is where you put the sensors inside a borehole, which is you can do that with a fiber optic cable, and that's also developed in other parts of the world. It goes by the name of distributed acoustic sensing. So it's a very fine fiber optic cable, very, very miniature, and you have a laser system that fires pulses into the cable, and it's able to sense seismic waves as they pass through with high precision. So it's something that is very useful because you don't have to occupy the well because it's a very small thing. So it's out of the way of the fluids that are flowing and all this stuff. So you can put those cables in production wells, injection wells, are out of the way. Even if they are super noisy, when these fluids are flowing and making a lot of noise, you still can get the results. The problem with that in Brazil, again, is that we don't have yet demonstrated the technology of putting these fibers through the wellheads, because they're different here. So that will come. One day we'll have those cables in all the wells. I do show you examples here, if you can see them, that have been demonstrated. These servers can be acquired and they get good data. But this an image you get around the borehole. It's not a very large area. You have to have a few of those to cover your field, but you can do it too. And there are more things here, but let's just move on to this. So I said earlier that we can do 4D seismic. We talked about how. We have challenges because the signals are small. Why are they small? Because you have carbonate reservoirs, which are very hard rocks, and then inside they have pores, and in those pores is where you have the oil, or water, or gas that you're going to be injecting. So when you have stereostochastic reservoirs, they're softer. So when you are flowing things, the whole reservoir, the whole matrix and pores deform, and you can measure big numbers. In the case of carbonates, the matrix itself is very stiff, so it doesn't change very much when you flow the fluid through it. So the signal that you're looking for is small compared to other places. So if you want to measure it accurately, you have to worry about the signal to noise ratio. Signal is small, the noise better be even smaller if you're going to see it. So that is the big challenge. Small 4D signals. They are also changing rapidly because you're injecting different types of fluids. First you inject water and then gas, and these signals are with opposite signs. Okay, so you have something that cancel, and they have explanations here, but we don't have time to get into all of them. So we have signals that are interfering and canceling each other. So not only small, but canceling, so worse than that. So you need to have, again, very high signal-to-noise ratio. So that gets in the way. The image itself, they're trying to subtract. They're trying to get two images to be good enough so you can then subtract them. But if each of them is not good enough, you have another problem. Okay, that is the obscure problem. And of course, we already talked about the footprint. You need to have these vessels, the cable. How do you do it in practice? More issues. Cost is something that we have always a concern. If you want to do many surveys to be able to follow the fluids, it will cost you. So how do you make that cheaper so that you can have those frequent surveys? So you can see how the fluids are moving. I mentioned that you want to know before water or gas gets into your next well, to the producer well. Well, if you want to know, you have to be shooting these surveys frequently. Because if you wait years, you will get there before you shoot. So you got to do it more frequently. It is a rare thing. In the Gulf of Mexico, Shell has been doing surveys every 3 years in many fields. And that is enough for that area because they have water floods and that's good enough. You can fairly well predict where things are going to go. But here we really need more frequent. So you got more frequent, it has to be less costly. And of course, these surveys produce a lot of data. That's the thing about data assimilation. What do you do with all this data? So we can deliver surveys which are high quality and even low cost. But then the people will say, well, we don't want them because we don't know what to do with the data. It will take us 2 years to build a new model. We don't want the data, we don't need the data, we can't use the data. So this is another problem. You can have high quality, low cost data, but you cannot use it. So you have to also work on that. And these days, and everything that has to do with data assimilation goes by the name of machine learning. Okay, so yeah, we need to do better about that. All right, so this is a tour so far of the methods to acquire 4D seismic and different kinds of the issues that we deal to try to measure the data. What I need to talk about now is the demonstration that these methods are working. So this is a slide that is showing the test of 4D seismic in the Lula field. So you see there on the top left a map of the acquisition. It was done by Petrophysical in 2015 and 2017, so 2 years apart. I think they had planned a year apart, but then there was something and it became 2 years. That's already fairly frequent by these standards. And then the nodes are on the seabed. In that case, the area that was covered was 111 square kilometers, which is a sizable area. And it was an area which was, say, impacted, controlled by one platform. It's called the Lula Piloto. Lula is a field with many platforms. We talked about it already. This is one of the 7 platforms. This is the one where you did the survey over. So it was done 2015, 2017, repeated, and we get some images, and I will explain those in a minute. But we have some challenges. So there in the middle column, I talk about 4D processing. So what I'm trying to show there, it's the water column, we said is 2,000 meters. And it's very important to know what is the velocity of water, of sound in water. Because if it varies a little bit from survey to survey, and you don't know that, then it creates another type of noise. Before we talked about a noise when the sensor is not put in the same place, exactly. But if you are, as you are assuming, that nothing changes except the reservoir, anything that changes creates this noise. So in this case, the top figure shows the velocity of sound in water in 2015, and if you could read that, varies a little bit by about 1 meter per second. The line there is not flat, it has about plus or minus 1 meter per second, which is nothing, but it's enough to disrupt your signal, but the noise. The one in the bottom is the velocity of sound over the length of the survey, so this is over a few months, and you see there's a big variation, a big slow there in the middle. And this is because there was some current that went through or something. It just happens. And that change in water velocity introduces a noise in your processing. In this case, the way the surveys are shot, this time of 2 weeks or so was over the same part of the field. So that part of the field had this problem. Okay, so you have to find a way, you have to know that it's happening, and as you can see, we know because we have that plot, and you need to find a way to correct that. And it's not that simple, because you can say, well, I will just do my whole imaging with another velocity model acquired later that is a little different, like that. It's more complicated than that because that way you're correcting vertical shifts and then everything is shifting in 3 dimensions. It's something that is a complication that we have in the pre-solve. Primarily because the signals are so small. This thing happens everywhere in the world. You just neglect it. It's a small number, you don't worry about it. But here is important. So there are challenges.
the bottom left picture is the solution. I mean, this is the outcome. It's a map. We're not going to explain a lot here because it's still being worked. But it's a map of the difference of the signals, amplitudes between the two surveys. And their colors are roughly red and blue. And the blue is what we call the hardening. So the fluid in the reservoir has been replaced by a harder fluid. So if you have oil and it has been replaced by water, water is harder, stiffer. So that will create this blue. And the red is the opposite, when the fluid has been replaced by something that is softer. For instance, when gas has been gotten into that part of the reservoir. Okay, there are other combinations where you can get that, but roughly you have that. So the picture, that the little cross section that you have there, shows that between two wells, there's a blue signal connecting them. That means that there has been water connecting the two. And in this case, that's what the seismic tells you, but you also know it because you have the wells. You have seen the water from one well reach the other. In one of those cases that is sooner than you really wanted, one of those breakthroughs. So we saw water going, we can detect that, and now the seismic also tells you that. So if you had done the survey, not 2 years apart, maybe 1 year apart, the blue line, the connecting the two, maybe go halfway. Okay, so you can see, oh, it's to here, so maybe I should do something different. So you can see that this would work if you did it, over a large scale. So the plan now is to do the survey over all of the platforms. So not one, but 7. Okay, so we'll talk about later how you would do that. It's a much bigger area, can be done. There have been OBN surveys done in the pre-salt as big as that. So it is something that can happen. But of course, bigger, it will be more expensive. And you remember that, that's an issue too. Okay, so if you want to interpret the data, you have to connect with the rock properties. Because we saw red and blue, and that's fine. We have some interpretation, but that's not enough. So we have the problem of carbonates. So in the siliciclastic rocks, which we don't have here, things are much simpler. You have depth that leads to compaction. When you have compaction, you know something about velocities. You can very easily relate things. Carbonates are very heterogeneous. Porosity is changing. The shapes of the pores are important. We have models like you see that cartoon there in the middle. This is from Xu and Payne, and this is how a carbonate rock is built with pieces. The solid rock has all these minerals, calcite, dolomite, and then the pores that contain the fluids can be of different shapes. You see them round and more or lower aspect ratio, and you don't know any of that. And then of course you have to put fluids in there. All of that is a rock physics model, and you really need to understand that if you're ever going to connect your seismic measurements to what's happening in the world. So that is a big area, and that's why this problem is difficult to solve. You can measure seismic, we saw that, but then what exactly is happening? How do I know that this blue or this red means exactly that this much water went over there or not? That connection is something that needs work, and for that you need to know about the rock properties. So this is just to tell you that. I'm not talking about rock physics here, and I don't know much about it, but I know enough to show you this. So the good news about 4D seismic is that all these things that are varying, most of the things that are varying in carbonates, don't care because they don't vary with time. So when the pore shapes might be different from here to there, it'll be different today, it'll be the same today or in a year from now. They may be different, but they're not changing. So in the 4D seismic world, you have a chance to do better. Okay, so we can do fluid substitution, we can worry about pressure effects. We have another thing here called rock fluid interactions. So because we have carbonates, they are mineral, calcite, and it's known that gas and water react with that. So at least in the laboratory, you see situations where your matrix that we said was very stiff, it is stiff, but it can dissolve if you inject these other things. Okay, so you inject water and gas, CO2 in this case, it can be stiff, but it can be dissolved. So it's a big question. In the laboratory, you have a lot of examples where the carbonate rocks just dissolve, and then the reservoir disappears. But in practice, it's not exactly happening. So many things that are done in the lab need to be somehow extrapolated to the field, and that part is lacking. So those of you that are working in petrophysics, sure they're doing a lot of things in the lab, but you have to think about what happens in the field. So we're not sure exactly how that translates to the field. A lot has to do with how much fluid you're injecting. In the lab, in the little sample, you can inject a lot of fluid, and you don't realize that you're flooding that sample with its pore many times, whereas that will take maybe 100 years in the field. Okay, so you need to worry about that. That's a connection between the two. I don't want to talk much more about this. I have another slide, but it's a little too complicated, so I'll skip it. There are other things that you need to monitor. We talked about, so far, monitoring what's happening in the reservoir with seismic. If the reservoir is not very stable, for instance, because these interactions are dissolving a little bit, or maybe the pressure support that we assume is not as strong as you assume, there will be some compaction. This whole overburden will tend to compact. We assume that in the pre-salt, the rocks are so stiff that that will be a very small effect. We can neglect that. But maybe not. So as you're worrying about what could change, this is one thing that can change. And you can see that in this cartoon, how 4D seismic can do that. Because what happens is if your reservoir compacts, it will essentially stretch the overburden. So all of that is above it. If you compact a little bit, it will stretch the whole thing. Now here, of course, we have salt, which will easily stretch. So we'll not use a big signal. So there are lots of reasons where even that signal should also be small. So we struggle with measuring small numbers. But they could be big if the assumptions that we make are not correct. So I think to watch out. So one of the systems that Shell is working with can measure the subsidence of the seabed. In other places, in other basins, it's significant. It can be a few centimeters per year. Okay, really. In this area, we expect to be maybe 1 centimeter per year. So it's not very much, it's 1 centimeter per year. But do you have devices that you see there, that orange thing? Measures pressure. So it sits on the seabed and can measure the pressure, which means the weight of water from that point to the surface. Imagine that in a year, it changes by 1 centimeter. That little additional water is what is measuring, that pressure of that. And it can be measured. But maybe 2 centimeters can be measured. We need 1 here. So you have to worry about how you measure that, and there are techniques to do that. Something else to monitor. So I now come to these sensors that I talked about earlier. It's important because they connect to many things. So this is one system where you can put nodes on the seabed for years. And we call them on-demand ocean bottom nodes, semi-permanent nodes. And the technology that is involved is a node that you have today, but it's able to be switched on and off. There's a battery, so a node that you have today, the ones that last the longest, maybe 6 months, because it can only fit so many batteries. So the deal is, can I have that node with a 6 months battery, but not spend all the time? So if I go and do a survey that lasts a month, I'll only consume the first month. And then I come back when I want, turn the node on again, and I do another survey and I consume the second month, and so on. So that's one of the things that this node does. It can be turned on and off. And so they're laid on the seabed, and then by some means, in this case it's an AUV, you see there, it comes, and at some height, maybe a kilometer, it can turn all of them on. You do your seismic survey, and what that means is one vessel comes, shoots, and the nodes are not touched. And then once that is finished, the same AUV comes and approaches the node close by, about 5 meters above, and extracts the data from it by optical means. Earlier we were talking about how to get data out of nodes, that usually it's very difficult. This is one way. Okay, so the node will have to have a way of transmitting its data, and it has to be something nearby to collect it. In this case, optical means. So Shell's developing this project, and we'll hopefully have these nodes, and we can test them in the Brazilian fields. Okay? So you can do frequent surveys over 5 years. After the 5 years, then you have to change the batteries. So if somebody has a bright idea about how to make those batteries last longer, that'd be a good thing, because they can sit there longer, or they can record things for longer time. So not only a few surveys, but you can also do passive monitoring. So it's when you sit there and you just listen to the environmental noises. And that's a good thing, because sometimes there are microseismic events, things are shifting, and then you catch them. So the longer the recording time, the better. Something that Shell is working on. Okay, so now to how would you monitor a big field? This is the last thing I have. So this is the inspired by the Lula field, where we have 7 platforms. And these rectangles in color represent the area over each of the platforms. Okay? So there's 7 there. So the idea will be you go in the year 0, the beginning, and you do your survey of all of them, 7, and then you come back every year and you record where you need it. That in practice is not as simple as sounds, but conceptually we do that. So for instance, year 1, it shows that only the yellow and the red are repeated. The others don't need that for whatever reason. Maybe there was not a lot of production, maybe the engineers had some other decision. In year 2, you can see that we don't repeat the yellow and the red, but we repeat the blue and the green and the other one. So in some modular fashion, depending on what is needed. You don't really know what is needed, that's why you're doing it, but if you need to schedule in some way, you'll say, okay, I will hire a seismic vessel by contract for 1 survey per year. Okay, so the company knows they have a job every year, and then how many of these patches they will do, we'll tell you later. Okay, so they know they can commit for that. That's a good way of lowering the cost. You can introduce new technologies here. Those different color patches could also be instrumented with these other nodes that we just talked about. Okay, so instead of having to bring every time the node system, you can just leave them there. You could also use small sources that we didn't talk about here too much, where you can then do the survey more quickly, because 2 boats are working at the same time. Okay, that cuts the time in half, so you can do that too, and things like that. Okay, so last slide. This is the summary here. The pre-salt in Brazil is growing. Lots of operators, lots of platforms being installed, many wells being drilled, and a lot of activity for the whole chain, people, and resources, and everything. And we need to help with that. So seismic monitoring is my topic. And we need to have to deal with the small signals. We need to have to deal with crowded, everybody wants to do the survey at the same time. How do you manage that? We need to interpret the data that we get. All of that has to be worked on. It's part of the system. So that's what I was talking about. We have lots of complications. We're not sure how the reservoirs behave. We don't know about this thing about the reservoir being stable with time or not. Many questions. Geomechanics, I touched on that a little bit. So how do we know that the seafloor or the reservoir is not deforming? There are other things that can happen. You have fractures. Some of these reservoirs are known to be fractured. Okay, we don't talk about this today. So when injecting water or gas, they may have some preferential direction where it wants to go. So you will also need to know that. And this is the topic of geomechanics. So in the future, we'll have lots of things that I think are going to help with this monitoring. I talked about all of them, I think. And then we really need to work on linking the petrophysics and the geophysics. So this is the rock physics. And I think that is coming. There needs to be more work, more laboratory work connected to the field. And I think that will grow also because all of these companies that are operating the fields also want to know. So they have to install their own labs, or they have to just have more services or something. All that will grow with time. Okay, that's all I have. Thank you for your attention.